Today I'd like to go ahead and talk about a problem that I wrote for the IEEE Xtreme 8.0 contest. The problem is back to square one. There is a link to the problem description, and if you haven't already read the description, I encourage you to go ahead and take a look at the link. What I'm going to go ahead and do today is we're going to talk about the problem, the format here of the input and the expected output. Finally, we'll talk about the approach to solving this problem. All right, so with back to square one, the idea is we are playing a game, and on the first move of the game, you move to the first square, and then each subsequent move you advance to the next square with a certain probability, or you go back to the very first square. In the example that's given then, we start in square one on turn one, and we would advance here to square two with a probability of 0.5. Of course, the remaining time, 1 minus here, 0.5, right? The other half the time, we stay in square one. In square two, then, we would advance to the final square, square three, with a probability of 1/4. 3/4 of the time, we go back to square one. So I assume that you've read here the problem and you have read through the specification of the input. Let's go ahead and take a look here at the sample input then. Okay, so for the sample input, the first problem that you're given, we are told that there are going to be 3 squares. So that's the first number is the 3, the number of squares. The next line describes the transition probabilities. So the probability of transitioning from square 1 to square 2 is 0.5, and the probability of transitioning from square 2 to square 3 is 0.25. This is exactly corresponding to the example diagram in the problem. For this test case, we're to output on a single line the number of expected turns needed to win. So I claim that the answer for this particular test case is 13. If we look then at the next line of the input, it's a 0, meaning that this is the end of input. The way that we're going to go ahead and approach this then is to go ahead and take a look at this game from the last square here back to the first. And for each square, we're going to go ahead and think about what would be the expected number of turns that we land in this square. Now clearly for the last square, the expected number of turns is going to be 1. Because as soon as you end in this square, you're done, right? Now if we think about that, and then we go back to the square before it, since we have to land in square 3 exactly once, and there's a probability to get from square 2 to square 3 of 0.25, we would expect that the number of times that we end up in square 2 in order to get to square 3 one time would be 4. Right? If we're in square 2 here 4 times, 1 out of 4 times on average we get to square 3, then this works out, right? So in other words, what we did is we said, all right, the expected number of times we end up in square 2, it's going to be equal to 1 divided by the transition probability here to get from square 2 to square 3 times the expected number of times we end up in square 3. All right? Now similarly, if we need to get to square 2 on average 4 times in order to win the game, we're going to need to get into square 1 8 times, because only half the time that we're in square 1 do we end up going to square 2. So the expected number of times that we'd end up in square 1 would be 8, right? And the formula that we used to go ahead and derive that was 1 over p sub 1 times E2. So then, what's the solution to the problem? It's simply the expected number of times that we're going to be in square 1, plus the expected number of times we're going to be in square 2, plus the expected number of times you're going to be in square 3, 8 plus 4 plus 1, or 13. Just to go ahead and convince you that this approach works, let's take a look at another way we can calculate, now that we have all of these these values in there. Another way we could go ahead and calculate the number of times that we're going to end up in square one. So the number of times we're going to end up in square one, there's one time at the very beginning of the game, right? We have to go into square one here at the beginning of the game, and that takes one turn. In addition, when we're in square one, 1 minus p sub 1 of the time, or 0.5 of the time, we go back to square one, right? So half the time we're in E1, we end up going back to E1. When we're in square two, if we look at this, we see that 3/4 of the time we end up going back to square one. So we have our formula. We can go ahead and plug in the values that we have. So what we're saying is that we have 1 plus 1/2 times E1. E1 is 8. Plus 3/4 times E2. E2 is 4. All right, let's see. That's 1 plus 4 plus 3. And what do you know? That equals 8, which is exactly what we expect. All right. So now, armed with our approach here to solving this problem, let's take a look here at the cases in the sample input 2. So we have one case in sample input 2 where we go into square one here, and then the transition probability is 0.5 to go into square 2. Right? So the expected number of times that we're going to end up in 2 is going to be equal to 1, because that's the final square. The expected number of times we end up in square one is equal to 1 divided by 0.5 times E2. This transition probability there, right? So that this is just going to be equal to 2. And then we add up 2 plus 1. And that's how we end up with 3. Okay, so let's go ahead and take a look at the last one. The last test case here. This last test case has got this additional issue here, that this implementation detail that we need to worry about, which is taking care of the rounding. All right, so let's go ahead and try to solve this problem. We've got state 1, state 2, state 3, and state 4. I'm only going to draw the forward probabilities because the ones going back to state 1 aren't going to be used here in the solution. So we have 0.3, 0.2, and 0.1. So let's go ahead then and calculate the expected number of times we're going to be in each of these different states. All right, so we're in state E4 one time, of course, right? The expected number of times that we're going to be in state 3, or square 3, is going to be 10 times. Okay, we just take the 1 times the 1 divided by 0.1, so it's going to be 10 times. The expected number of times that we're in state 2, this is going to be, okay, 10 divided by 0.2, which is 50. And then finally here, the expected number of times that we're in E1, this is going to be equal to 50 divided by 0.3, which is 500 thirds. And let's go ahead and convert that to a mixed fraction here. So we have, we come up with 166 and 2/3. And if we add up all of these numbers, we get, all right, 61, 227 and 2/3. Now, taking care to round, then we would come up with the expected output of 228. So I hope you found this explanation useful for this problem, and I hope you enjoyed the problem. You can feel free to go ahead and try to code up a solution. If you have any questions, I'm happy to go ahead and try to answer them for you. You can either leave a comment on this video, or feel free to send me an email. My email address is bloom@psu.edu. That's BLUM@psu.edu. Thanks.